The work that I will talk about today was done in collaboration with my colleagues at NICT, Fumiki Yoshihara, Tomoko Fuse, and Koichi Semba, as well as Naoki Yamamoto from Keio University, and also the group of Adrian Lupascu here at IQC. And I will talk about two topics related to optimal control of multi-level systems, more than qubits. First, I will talk about optimizing qubit control, and then I will talk about doing two-qubit gates when the qubits, actually the devices that we use to implement the qubits, have higher levels, and we have to keep these levels in consideration when we optimize our. So we usually think about superconducting qubits in our work, and superconducting qubits have a number of different designs. So in some designs, you have, so the qubits or these devices, superconducting devices, always have many energy levels. In some cases, you really have two energy levels that are close to each other and very far from everything else. The third energy level is very high in energy. So you can completely ignore its existence, and you really work with this device as being a two-level system, so a really good qubit with a two-dimensional Hilbert space. With some other superconducting qubit designs, especially some of the recent ones with good coherence properties, they are almost harmonic oscillators with a small nonlinearity. Then if you want to use this device as a qubit and use only the lowest two energy levels, 0 and 1, then you have to be careful not to excite the higher levels. And that usually means you have to drive the system weakly to avoid non-resonant excitations of the third and higher levels, to avoid the leakage. So that's usually the way you deal with these qubits. But also you can say, well, if I have these higher levels, I can use the device as a QuDit, Q-trit, Q-quart, and so on. And just to give you a few examples of things that have actually been done with superconducting qubits. So it has been recognized actually for a long time in this field that you can use the higher levels to modify the energy level structure in the qubit space and simplify the implementation of two-qubit gates. And this has, in fact, been used in a number of experiments. And then in 2009, there was also a nice experiment from John Martinez's group where they used the phase qubit, which is, again, one of these weakly anharmonic qubits, to simulate higher spins, not just spin 1/2, but spin 1 and spin 3/2. And also, you can use QuDits to do tests of quantum mechanics. So we all know about Bell's inequality of non-local realism. But also, when you have qubits, for example, you can test the Cohen-Specker theorem or contextuality. And the nice idea here is that in quantum mechanics, the outcome of a certain measurement depends of a certain observable depends on whether or not you measure another observable. And this can be counterintuitive even from the quantum mechanics point of view. So if you take a qubit, the operators Sx squared and Sy squared, they commute. So usually we think that there is no conflict between them. But actually, if you measure the two in opposite order, you get different results. So the order that you make the measurements, or whether you measure only x squared or you measure Sy squared before it, you get different results, which even accepting quantum mechanics sounds counterintuitive because these operators commute. And we think of them as not interfering with each other. So now, in the experiments that we did in collaboration with Adrian's group here at IQC, so they have a device that is a capacitively shunted flux qubit. So there were 3 energy levels that we used to implement a qubit. And here we asked, OK, we want to implement a general qubit gate. So what is the best way to do that? And a number of talks this morning and this afternoon also mentioned this decomposition into Givens rotations. So if you have a qubit, you can implement any operation on the qubit, any gate, as a sequence of 3 kind of qubit gates. So first you drive the 0-1 transition, then you drive the 1-2 transition, and then you go back to the 0-1 transition. But by adjusting the parameters of these 3 rotations, you can get or construct any qubit operation. And you can generalize this also, as previous speakers have explained in detail, to a QuDit, not just a qutrit. So you kind of keep going up and down the ladder of these transitions. And for a general QuDit with a general D, you get quadratic scaling of the number of pulses with the number of energy levels. So you get this D times D minus 1 over 2 pulses to implement the general QuDit operation. And then we said, OK, let's look for a single pulse implementation of a QuDit gate, and in particular, a qutrit in the experiment. So if you think about, OK, you are given a unitary operation, a 3 by 3 unitary for a qutrit, you can say, if we want to get this out of Hamiltonian evolution, the propagator is e to the minus IHT. So if you take the unitary that you want to implement, you just take the logarithm of that matrix, and that tells you what the Hamiltonian should be. So up to a constant, which is the time here, you know what the Hamiltonian is simply by taking the logarithm. And then mathematically, you can say, OK, this Hamiltonian, which will also be a 3 by 3 matrix, can be decomposed or constructed from the 8 Gell-Mann matrices. And then using these matrices, we can construct any Hamiltonian. And then from an experimental point of view, you can say we have 3 transitions. So we have the 0, 1, 0, 2, 1, 2 transitions. We drive all of them at the same time. So that's 3 drives for 9 drive parameters in total. You have the 3 frequencies and amplitudes and phases. And there is 1 overall phase. So you get the 8 parameters which you expect to get to generate a general qutrit operation. So that all makes sense. And then one complication that comes up, usually with superconducting qubits or qutrits, we like to keep the frequency, the driving frequencies fixed at the resonance frequencies between the energy levels. So then the frequencies really are frozen to the resonant frequencies. So that makes us lose some of the drive parameters. And then we have to compensate for that somehow. And the way people deal with this with qubits is we can implement any qubit gate, actually. So now we think about qubits, just 2 energy levels. And we drive always resonantly with the 0, 1 transition. So to implement any qubit rotation, we decompose it into 2 rotations. One that is kind of represented by the diagonal matrix. So that's a rotation about the z-axis. And that can be implemented simply as a phase shift in the drive fields. And then we have a purely off-diagonal matrix, which can be obtained by resonant driving. So this is a standard decomposition for qubits. And then we say, OK, let's try to do a similar thing for qutrits. So we think about driving all 3 pairs of energy levels, all 3 transitions. We drive them resonantly and say, can we decompose our qutrit operation? And we take one example. And we actually tried many different random unitaries and asked, can we decompose them similarly to the qubits into a diagonal part and a purely off-diagonal generator part? And then we do a search, numerical search, for whether this decomposition is possible. So to me, at least, it was not immediately possible. Intuitively, we thought, OK, based on qubits, we think that it will be possible, but it was not immediately obvious. And then we did the numerical search, and we found that indeed you can always decompose any qutrit unitary in this way. And it turns out that the decomposition is not unique, which I also do not understand. So mathematically, I don't know why the decomposition is not unique. We found for the Walsh-Hadamard gate, which we used as an example, we found 5 different decompositions that we cannot relate in any trivial way to each other. And then we did the experiment, as I said, for the Walsh-Hadamard gate, and we got a gate fidelity of about 99%. And I think Adrian will talk more about this later, right? So now I will move on to the second topic in my talk, and that is the speed limits of qubit gates, 2-qubit gates, but keeping in mind that the devices have higher energy levels. So now, if we think only about qubits, we have 2 qubits coupled to each other with a fixed coupling strength. And then we drive the 2 qubits. We apply microwave signals or can be anything to the qubits to implement a CNOT gate, which we use as an example of a 2-qubit gate. And we want to know how fast we can get the CNOT gate. So we use optimal control theory, numerical optimal control theory, and usually these algorithms of optimal control theory, you give them a pulse time and what part of the Hamiltonian is fixed, and what operators in the Hamiltonian are tunable, and their coefficients are then optimized by the algorithm to give you the maximum possible fidelity relative to the target that you are trying to achieve. And then, so the algorithms usually maximize the fidelity, but we can use these algorithms to find the minimum time that is needed to implement a certain gate. So as I said, the CNOT gate in our case. So the way you do that is you start with a short pulse time, and you find that the fidelity remains small because you don't give the system enough time to implement the 2-qubit gate that you want. Then you start increasing the pulse time that's moving right along the x-axis, and you see the fidelity goes up and up, 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 until it reaches 1, and then it becomes flat. So if you have enough time, you can implement a perfect CNOT gate, and more time doesn't hurt. But less time makes it impossible. So usually you define a threshold, a few nines, and you say, OK, if I go above this threshold, that's exactly this point is the minimum time needed, or this is the speed limit needed for our CNOT gate. And now we want to study this problem for a weakly anharmonic qubits. So we take, again, 2 qubits, but each one has higher energy levels. And we have to keep in mind these higher levels. We have to take them into account when we do our calculation to optimize the pulses and calculate the minimum time. So, OK. So we use one of the standard optimal control theory algorithms, the GRAPE algorithm, to optimize the pulses and then use that to calculate the minimum gate time. So we have a weakly anharmonic qubit for each of the 2 qubits. And then we truncate. We say, OK, let's keep 4 or 5 energy levels for each qubit, and then do the simulation to find the CNOT gate. And actually, a very nice idea that came out of Waterloo about 15 years ago, maybe, is drag, where you suppress the leakage to higher levels by actively driving the system. So you drive the 0-1 transition. That's the transition you want to drive. But you will get off-resonant leakage transitions to level 2. But then you actively drive the 1-2 transition on resonance to exactly counter the effect of the 0-1 driving. And so you constantly suppress the leakage to state 2. But then, in our case, we say, OK, we don't really care what happens at intermediate times. You can leak out to level 2 at the intermediate times. The important thing is that at the end of the pulse, you want everything back in the qubit space. So we don't penalize exiting this space or departing from the space at intermediate times as long as we refocus and come back at the end. So we, again, set up the GRAPE calculation. We set the target as the CNOT gate. And here, one technical point is that in the GRAPE algorithm, the target should be unitary. But we don't care what happens outside the qubit space. So we put ones here. You see we have a unitary in the qubit space, but we put zeros everywhere else. So this is not a unitary operator. But the nice thing about it is it doesn't penalize whatever happens outside the qubit space. So any pulse that starts from the qubit space and ends up in the qubit space with a CNOT gate is equally acceptable. And then we run these calculations, and you can first look at the red squares here. This is when we have only qubits, so we don't have any higher levels. As I said before, the fidelity goes up until it reaches 1, and that gives us the minimum gate time. So the minimum time should be 1, but because of some numerical errors, convergence, basically, it reaches 1 a bit later. Now, when we add higher levels, intuitively, we think of the higher levels as leakage levels. They are bad. They force us to drive weakly, so they should slow down the gate. But we find that when you add higher levels, you can get the gate actually faster. So what we think of as leakage is somehow helping us. And even though this is at first surprising, when you think about it, if you think of these qubits as harmonic oscillators, actually, if you excite the harmonic oscillators to higher levels, then they interact more strongly with each other. So you have this interaction term, the G times the X1, X2 operators. Then these scale as the number of excitations. I mean, the square root of the number of excitations in the first qubit and the same thing for the second qubit. So you have stronger coupling in the higher levels. So it turns out that the best way for you to do the CNOT gate in the qubit space is to excite the two qubits as high as possible, let them interact in the higher levels, and then at the end of the pulse, bring the qubits back to the qubit space. So to confirm that this is indeed what is happening, we plot here the probabilities. The red line is the probability to be in the qubit space. At the beginning, it's 1, and at the end, it's 1. So as we want, at the beginning and end of the pulse, everything is in the qubit space. At intermediate times, we see that this probability goes down a lot, and the probability to be in the highest level is actually the maximum. So that agrees with the intuitive explanation that, yes, you gain by exciting the qubits to the higher levels to get to the stronger interaction, and then you bring everything back at the end of the pulse. But then if we think about this a little bit more, we say, OK, if we have strongly anharmonic qubits, so if these transitions, all of them can be addressed independently of each other, that's a good idea. You excite the qubits to the higher levels, they interact strongly, then you bring them back. But if the qubits are weakly anharmonic, you cannot simply say, OK, I'll truncate the system after 4 or 5 levels, because when I'm driving very strongly to do this fast pushing up and down the state, then there will be uncontrolled leakage to the higher levels that we ignored in our model. So then we really have to be careful. And then we say, OK, let's try to penalize going very high up this energy level ladder. So we will not penalize going up 1 step, but going up 2 or 3 steps, we will put a penalty on that. And let's do the calculations again. So we, again, repeat the calculations. And now to penalize the occupation of the higher levels, in the gray calculation, there is a simulation step where you simulate the dynamics. And then we add these loss terms that if you occupy some of the levels that you don't want to be occupied, you put a loss term that the probability basically disappears. So the wave function decays. So again, this is not a physical process because it doesn't conserve the normalization of the state. But it turns out to be a mathematically and computationally convenient way to put a penalty. It doesn't complicate the simulation. We can simulate real relaxation and dephasing. But that takes you to a larger computation. Instead of dealing with pure states, basically, you have to deal with density matrices and mixed states. So this method keeps the computation simple, fast, and adds a penalty. Mathematically, it's a penalty that works to the effect that we want, that it looks for pulses that do not excite the higher levels. So again, we repeat the calculation. And first, you can look at this plot. This is now the occupation probabilities of the different spaces. So now the probability to be in the qubit space remains very high. It doesn't go down as before. And the probability to go up 1 state, which we did not put any penalty on, it's significant. The state that we penalized, again, you can hardly see a bit of population in it here. So this modification of the algorithm works. And now we again go back to the intuitive picture that the higher levels actually are leakage levels. To avoid leakage, you have to drive weakly. And so the time that you need to complete the CNOT gate becomes 4 or 5 times the reference value. So 1 is the value for qubits if you don't have these leakage levels. So when we added this penalty to excite the system, we have the higher levels, but we don't want to excite them. You have to drive slowly. You have to take longer time to do your CNOT gate. This is different from the previous result that I showed you, that if there is no penalty on going up, you can do everything in a controlled way. You can actually benefit and speed up the gates by going to the higher levels. So everything is consistent and makes sense. And now to summarize, I first talked about designing and implementing a single pulse Q3 gate in the first part of the talk. And the second part is we calculated the speed limits of 2-qubit gates when we take into account the higher levels. and found that you can get a speed up or slow down depending on the different parameters. So thank you very much for your attention. Yeah.